Organ donation is unique in its existence in medicine because it is one of the only treatments where the remedy requires another human being. But with an ever-increasing need for donation and certain wait lists surpassing 7 years, the ability to generate these life-saving organs could revolutionize the current medical landscape for numerous treatments. 3D bioprinting may be able to provide this relief, as tissues, organelles, and even certain organs have been able to be printed and human clinical trials are underway. However, every scientific breakthrough comes with its own set of ethical and social problems when integrating into the world we already know. So how close is this new future? And how will we navigate it? Welcome to BS, a podcast where we take an in-depth look at different scientific and social phenomena and innovations whilst tying them back to broader societal perspectives and why you should care. Come along as we explore 3D bioprinting and the medical advancements it could bring. First time I ever encountered or came into contact with the idea of 3D bioprinting is when one of the graduate students in my lab actually came back from a research conference, and he said that he actually was able to hold a 3D bioprinted human heart in his own hands. Obviously they didn't tell him what the material was made of because it's proprietary. They was not gonna let anybody mess with that bag, but honestly, I mean, it was so cool to me because I didn't even know that this was a technology that existed or was even being developed. But at the same time, I feel like that would freak me out, holding a heart. And, it's not a human heart technically, but it's still, made with very similar materials.
Honestly, one, crazy. But also, too, I think the first time I came across 3D bioprinting was just obviously my major. And also, I had a minor in neuroethics, so they were always bringing up 3D bioprinted organelles and the tissues and what if they 3D bioprint a brain? I was like, all right, y'all, let's calm down. I mean, it could be in our near future, but yeah, they were always talking about the other side of things, the ethical complications of bioprinting and bioethics, which is very understandable because it's the idea of being able to create a part of a human body just in a lab, a significant part an organ, is definitely,
it's very futuristic.
Real sci-fi.
Yeah, no. And I mean, I love this topic because my work in a lab was specifically tissue engineering, regenerative medicine. So I'm okay, this is a topic I actually kind of understand. I'm reading the research articles, the background for the papers, and I'm understanding. I'm I love that for me. So
honestly, great. Because, listen, you the one with the biomedical engineering degree, fighting for my life doing this research, so, you'll lead us through. So, as we've started to do, we just wanted to have some guiding research questions throughout the podcast so you guys can follow along with us a little bit easier and understand everything we're trying to explain. So, first, we just wanted to talk about what is 3D bioprinting and how can it add to the current technologies in engineering and medicine. Second, how does this technology actually work? Third, where are we in the research and development and what roadblocks currently exist that prevent 3D bioprinting from scaling up? And lastly, what are the ethical concerns that may arise from 3D bioprinting? So go ahead and take it away. Start us off, biomedical engineering. What is 3D bioprinting?
And yes, this is a pretty technical episode too. So if you see us glancing down at our computers for the people who are looking at video, it's because we're making sure we're reading our notes and stuff like that. Because once again, we never give you misinformation.
Make sure we're not just making it up.
So. Exactly. Check them sources. But, okay, what is 3D bioprinting? Simply put, 3D bioprinting is just using 3D printing techniques with biological materials to create functional 3D structures such as tissues and organs. One article from the NIH literally stated that 3D bioprinting is an emerging technology expected to revolutionize the field of tissue engineering and regenerative medicine. So we're obviously seeing very, very bold statements made about the impact of 3D bioprinting and what it could do for the state, our current state of medicine and science. And why is it important is another thing. I mean, obviously, as STEM nerds, we love scientific innovations just because they're scientific innovations. Like, it's always cool to see how humans can push the bounds of what we're capable of. But at the same time, there really is a need to increase the amount of tissues and organs that are present in the world because sadly, the amount of people who need an organ and the amount of people who are willing to donate one, or the amount of organs that can be properly be harvested for a transplant are not matching. As of June 11th, there were 105,524 people on the national transplant waiting list, and it's estimated that around 13 people die each day while waiting on an organ transplant. So these are really, really huge numbers. Once again, so many people in need, but not enough organs to really fill that gap. And we're constantly seeing how people are reaching out, like, be an organ donor, please be an organ donor.
It's crazy. I even remember, like, at my school, there used to be like this huge billboard right outside of my parking deck of this guy just basically saying like, I really need a kidney. And like, I don't blame him. Like, as a donor myself, the process is madness. Like, one, and I guess I can only speak for kidney donation, like dialysis is hell. Like, and it's honestly not going to sustain you for a long time. The kidney donation list is one of the longest lists there are, and the process of donating, especially if you're a living donor, also hell. Like, so there is any capacity to one increase the available like organs, like even though again we're talking more a little bit more into the future, or to not need donors living or dead, because again the majority of people, the way they die, they're not going to even be able to donate. Like, it usually requires some kind of cardiac or brain death where the rest of your body is still working in order to use the organs, because like they still need to be, you know, up and kicking. So yeah, this is definitely going to be incredibly important and very revolutionary technology if they're able to pull this off. Like,
yeah, no, the possibility that we can not only create tissues and organs, but also personalize them to the patients that need them, that reduces the risk of organ rejection and improves the success rates of transplants. And then on top of that, they can just be used for biological models in general. So that could be developing new therapeutic approaches, testing medical devices, studying certain phenomena that we couldn't do with live human beings, or where there are ethical concerns for live or dead human beings. So it really opens up like this wide array of possibilities and elevates us to a whole new ball game in terms of what we can do with biological models. So
the possibilities are honestly endless. Like, not to sound like the nerds we are, but this is going to be one of the biggest things in science in the next century.
Oh, for
like,
sure.
That's how I feel. So again, like, let's go back to our guided research questions. Turning to Ileana,
like, you're killing me, bro. Okay.
Actually, I can start with like how the technology actually works, but again, when we start getting into it, just know who to call. So 3D bioprinting kind of works very similarly to just regular 3D printing, and the main difference is the Bioink and basically the material that is actually used to make the organ or the tissue. The Bioink is usually made up of like hydrogels and the cells that put them to, like, and the cells and the hydrogel kind of helps hold the cells together, so it, the living thing can continue to develop, which we'll get into later. And basically the type of 3D printing that bioprinting usually uses is additive manufacturing as opposed to subtractive. And with additive, you're kind of just like building it up layer by layer, usually bottom up, whereas for subtractive, you usually have the material and you kind of carve away at it. So most of the type of methods we're going to discuss are going to be like additive bioprinting. And again, like, most important difference, instead of like plastic, metal, and other objects, they're usually swapped out for like polymers and biomaterials that are one, biodegradable, two, more compatible with the human body, and three, able to actually generate and grow, which is why we're, you know, saying polymers, hydrogels, cells.
So the first step to create a 3D biological model is you will either create a CAD design or do medical imaging. So first of all, even like making this, I realize it's been a while since I 3D printed something. So I need to re-up that skill again. But basically there are a lot of different CAD softwares out there, but there are actually certain CAD softwares that are specifically being developed for bioprinting. So there's BioCAD, Tinkercad, Cadia, etc. And obviously those are through like the main big manufacturers like AutoCAD and stuff like that. You would convert the model to an STL file, and to like simplify it for anybody who doesn't know about 3D printing, an STL file is just what the printer reads to know how to actually build up whatever you're printing, basically. And there are three major methods for printing. So, gold.
So three major methods are inkjet, laser, and extrusion based. And also, this is just the three major methods for bioprinting specifically. Inkjet is like also called material jetting. Is basically using the droplets and depositing through a nozzle. A lot of them are going to be like that. And basically putting that onto a printing surface, and there's something that's usually like forcing the droplets through. And again, the droplets will be of bioink, which are usually the hydrogels and cells needed to continue to grow whatever biomaterial they're making. Mm-hmm. Then we have laser, which is a little bit different because it takes like laser pulses to deposit the bioink droplets, and it takes it from a donor material and it usually puts it to a receiver material, which is usually like a biopolymer or like a cell culture medium, again to allow the things to grow. And then lastly, we have extrusion based bioprinting. Basically, like it extrudes the bioink out of a nozzle, but more so like in continuous strands. I feel like this is the method of 3D printing I see online mostly, like when I actually see somebody do it. And again, it's kind of like building it from the bottom up, and that's how it creates like the 3D models. Depending on what they're trying to make, how much they're trying to scale it, they may use different methods, which is why there's three, but there's definitely like pros and cons to each of the methods.
So for inkjet printing, I mean, it's similar to traditional inkjet printing, like through the droplet method. The pros are that it allows for very high resolution. It can be anywhere between 10 to 100 micrometers, which is really, really good and better than the other two methods of printing. It's also high speed, low cost, high cell viability. So think of it as like, I don't want to say like the cheap printing option, but it's really good for just kind of like getting something out there and getting something on paper. But the cons is that it's not as flexible. The ink must be a very specific viscosity, and the low viscosity to be ejected from the small nozzle makes it so that it can only really do certain kinds of bio ink and not like I said, as flexible as other kinds. Laser is really cool. It has higher cell viability because there's no stress caused by the interaction between the dispenser and the bio ink. And what I mean by that is obviously cells are very, 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 very sensitive. So if you're feeding cells through a nozzle, there's going to be shear stress that is going to lead to some of them being killed. So laser kind of discontinues the need for any shear stress. And it's compatible with a lot of different bio ink types and a wide range of viscosities. But because laser is so good at its job, it's more expensive, and it's also just a more complex method to use, which is why it's not as widely adopted. And finally, extrusion-based bioprinting. You can also print a wider range of biomaterials with varying viscosity with this one. It's also a bit more affordable and scalable, but the cons are that it also causes that shear stress due to the interactions between the dispenser and the bioink, and also higher viscosities can result in lower resolution. So basically, the more expensive it gets, the better the resolution usually, but yeah, it ends up being more expensive, more complex. So we see inkjet and extrusion-based bioprinting being used more.
And guys, like, you don't understand, like, these living cells, they are incredibly fragile. Like, that is something that I feel like we should definitely, like, emphasize. Like, I remember when I was working in my first ever wet lab, like, as a job, and it was a lab focusing on, like, CD4 T cells and, like, their impact on like HIV and like the issues just surrounding that, because like certain people, they do not respond well to HIV medication, so they're thinking that there's something in their immune system, particularly their T cells, that may be the reason why. And I remember having to like, you know, get fresh bag of blood, still warm, and like taking, like trying to extract the cells from the blood and seeing the amount that were still alive. And this is just with my little two hands and like a centrifuge. I'm not gonna lie, it was not looking good for my cells the first time I tested it. Like, it was not looking good for them. So yeah, trying to figure out a way, like shear stress is inevitable, to be honest, but trying to figure out a way to like reduce the amount of cells that actually die in the process is a very important part.
Oh, baby, I used to kill myself when I first started working. It's not funny, but it is. It was not for the amount of class I would go through.
2 hours of work, I promise you, it's not funny when you scan it in that little thing. It's saying 63%. What do you mean by that?
Girl, I used to be checking for cell viability, and I used to think it was a practical joke. Like, there's no way.
Because what do you mean by that?
Like there's no way all my cells are dead.
I've been doing this for 4 hours. What do you mean by that?
But then you get discouraged. But then you do it again because that is the scientific method. That is how we learn to get better.
You be seeing that 91%. Like, I used to pray for times like this. Like.
But obviously the 3D printing seems really complex, but it's actually not even the main challenge in terms of bioprinting. The main challenge, as we've obviously talking about with these very sensitive cells, is going to be the bioink, which is once again used to create the scaffolding and the 3D models. And so bioink consists of two things. It's the biomaterial solution, and then the cells, and that can be either with or without growth factors. And to kind of simplify it, basically the cells are adhering to whatever is in the biomaterial solution. So once again, hydrogels that serve as the scaffolding for the model. And polymers are great for tissue modeling because they're both biodegradable and biocompatible, but they also pose issues because they're harder to sterilize and leachable in body fluids. And you can use two different kinds of polymers. So you can either use natural polymers, so think gelatin, collagen, fibronectin, alginate, chitosan, all of these different kinds, or a synthetic polymer. So that can be polyethylene glycol or PEG, shout out to PEG, or PEG Formel, PCl, PLGA, PLA, and these are all just different kinds of synthetic polymers for the biomaterial solution. In my lab, actually, we were one of the only people to work with a natural polymer. So shout out to natural polymer gangs, because we were using collagen, but everybody else was using PEG or PEG Formel. So that's my little fun fact. But there are actually some hybrid materials that blend natural and synthetic polymers to try to basically get the advantages of both. There's also another kind that people have been starting to use for the biomaterial solution. So this is decellularized extracellular matrices. Shout out to the extracellular matrix too, because I was also working with that. Like, love this topic. But basically, decellularized extracellular matrices have shown that they can actually support growth and function of different cell types after the original cell type was extracted. And DECMs from 3 tissues, cartilage, heart, and adipose tissues can actually be solubilized into bioinks and then subsequently bioprinted. And this is great because they contain characteristics of the extracellular matrix of the original tissue, which is going to make them a lot more adaptable to living conditions and less likely to be rejected. However, the low viscosity of DECM bioinks can cause issues with the accuracy of models and like certain mechanical properties. So there is still some tweaking and fixing that needs to be done there. And the way that they go about selecting what type of cells and growth factors they're going to pair with the biomaterial solution is by looking at key bioink properties that will obviously depend also on the type of printing method that they're going to use. So one of the properties is like printability. So that's the physicochemical properties like viscosity, surface tension, cross-linking that allows the bioink to be deposited with high precision and accuracy. There's also biocompatibility, like can the ink support normal cellular activity like cell growth and proliferation without causing an immune response, because that's obviously going to be an issue too. And then biodegradability, like can the cells basically reproduce at the same rate that the ink is degrading, and also can the ink degrade without causing any harmful byproducts either, because that's also going to be a problem, because you don't want the bioink to kind of be degrading in someone's body and then it leaves byproducts that are actively causing harm to other organs or human systems. So yeah, and then after we have gotten through the printing process, okay, we've chosen what type of printing method we're using, we've chosen what type of bioink, and now the model is created, boom. what do we do now? How do we make sure that it continues to be successful and viable? That's where we're going to use static cultivation, and that's the main method they use so that the scaffolds will develop. But basically, static cultivation is just leaving something in a container with a fresh nutrient solution at the temperature and pH that it likes for a certain time period so that it will grow. It's basically here. Like, I'm just gonna leave you. Like, imagine static cultivation like a human being. Like, I'm just gonna leave Ileana in her apartment with hot cocoa and some good books and a trashy reality TV show, and I'm gonna let her rot for 1 to 14 days so that when she comes out, she's fresh and wonderful and ready to attack the world. And that is basically what they do. And then they use different types of bioreactors where they host the models for scaffold maturation. And the type of bioreactor they use is once again going to be dependent on the type of tissue that they're engineering and the kind of physical environmental characteristics that they need. So that's a mouthful, of course. It's a lot to go through because obviously it's a very complex process, but it's such a cool procedure and such a cool thing to do, like be able to literally make like tissue like from scratch.
No, it is an incredibly complex process, especially because everything about the human body is so incredibly specific. Like even when they're developing these tissues, developing even like pieces of these organs, these organelles, like they have multiple different cells, multiple different factors going into them, and having to make sure like all of them are working correctly, like you're growing everything correctly. You didn't forget to like take it that thing out of the deli freezer. And, like, ooh, it's a lot.
I was struggling with my little T21 flask, babe. I was
working with maybe 2 types of cells, just sweating, like ooh. So yeah, like now that you understand like how they're actually going through the process of creating these biomaterials, how like where are we in research and development, and like what are the current roadblocks that exist that are preventing 3D bioprinting from scaling up? Because when you hear all of that, you'll be at the little like research meetings, hearing the new research sometimes even before they even drop the paper, and you're like, oh, y'all seem like you got it figured out, like so like when is that dropping? Like I used to be in those like neuro research symposiums, and I used to be like, wow, like y'all know all of that about Alzheimer's already? Okay. So like,
mind you, like when I tell you, I think one of my favorite fun facts is that I think like bench lab research takes 20 years to go to market or something like that. Like
those
it takes
studies,
so
they don't play.
long. It takes so long.
It's years, and that's if you even get approved to do.
Oh yeah, that's if you even get to the clinical trials, and then even then the failure rate of certain clinical trials, like they will shut stuff down quickly.
When I was in freshman year, because like a lot of the research that we learn in neuro is like junior, senior year. I was in freshman year, like, yeah, come on, let's go. Like, y'all got all this information? That's crazy.
The whole time, we're 15 years out from any real development occurring. Like,
my knees gonna start cracking before we get that research paper.
But, I mean, let that be a lesson. Research takes a long time. However, really takes a long time.
We will say, when it comes to, like, 3D bioprinting, it's not all futuristic. It's not all, like, sci-fi. Like, there's been a lot of, like, current, things that it's already helping and current developments that have already happened and have already cleared. For example, there's like we see a lot of the developments in animal testing, and even though it's like not a direct transfer, it's definitely a good sign that things are working. For example, like they've been able to create all 3 layers of skin, the epidermis, the dermis, and the hypodermis in rat models. So they basically create the dermis and the hypodermis. But for the epidermis, after those 2 are created, the dermis will just generate the epidermis within 2 weeks, which is great when you think of things like skin grafts, when you think of things like researching on human skin, like being able to like start to develop pieces of whole organs.
2
weeks
like, is a quick time.
Yeah.
Especially when I'm thinking of like burn victims and stuff like that. Like I feel like this would be really good for skin.
This would be great for
grafts,
them. Yeah. And especially skin grafts, and like being able to create that could be a replacement for animal testing, which we're like now seeing in the EU.
Okay, ethical concerns.
Like,
finally the mice are free, bro. Or well, we'll see, potentially.
I was about to say, like,
I know they looking at this like, please please go to market.
Baby, those rats and mice ain't gonna be free until them organs start pulling up. I'm not even gonna hold you. We're still using them for the bioprinting. But yeah, the IBIC was just the Institute of Bioengineering of Catalonia, created Brighter, which is funded by the EU, and it's basically a project which is set on trying to reduce the amount of animal testing that we're using, and 3D bioprinting is one of the ways that they're doing it, by being able to create like human skin grafts as replacements for using animals to test things out on. So yeah, there's that potential in research, helping those little poor animals out. Like anytime I used to go downstairs to the basement and see the little mice and rats we have in that little dungeon, I just feel so bad for them.
I didn't even have to go to the basement. Every once in a while, I would just walk out into the hallway, and it's just some random lady wheeling like these incapacitated mice, just spread out on the floor around. And I think I don't know what I expected from animal studies, but I think within working for a couple of months at my lab, I found out that like every animal that is in a research study is put down.
Oh,
like,
yes.
Regardless of if they survive or not.
Sure.
And they were like, because of just like you have to put them down. And like it makes sense, but at the same time, it's like, oh my God, like these poor little.
I really feel bad. Like you're taking them out back and shooting them. But like they don't, obviously they can't release any tampered animal back into the wild because we don't even know what that's going to do to the ecosystem. I think there's issues with long-term consequences of the things we be doing to them, because I'm not gonna lie, y'all, they be doing anything to those animals, but
I be staring at them like you don't even know what your future is. I'm like, oh.
And yeah, so there is that like research perspective, and there's also like a clinical perspective, like Ileana mentioned, like skin grafts. It can be very useful for that, especially with burn victims, because oftentimes like they take a piece of your own skin, so now that you have another like scar or another area that is kind of like, I don't want to say messed up, but altered in order to fix some other issue, but if we were able to just like, take your cells and develop your skin again, we wouldn't have to do that. This would also be very helpful for trans people who are going through surgery, because for certain bottom surgeries, they do take like usually a piece of your forearm to use to create your usually new appendage. So if they're able to just generate that, that would also be quite helpful. There's a lot. We need skin honestly often. So there's like a lot of potential for that too. And particularly for humans, human organs have always been on like the development. Well, let me not say always, but definitely within the last like 25 years, within the 2000s. In fact, in 1999, Dr. Atala, he 3D printed a bladder for, I think, a 13-year-old who had spina bifida. And basically, their dysfunctional bladder was causing them to have issues with their kidneys, and was causing their kidneys to fail. They were on dialysis, like I said, terrible. So being able to, 3D print him a new bladder, and he's a grown man till this day. He's still using that bladder that they 3D printed.
Good for him.
And he's living a quite normal life, actually, and does not have to take immunosuppressing medications, because it was created from like his own cells that it's not going to reject. Like this is the type of things we talking about. Like keep funding science, guys. Keep funding science. It's important. Don't let them tell you anything different. It's important. Like
scientific innovations being used for good. We love to see it.
Yeah, like and we even saw recently in 2023 a 3D printed organ was transplanted to a South Korean woman in her 50s who actually lost part of her trachea, which is like your throat, to thyroid cancer. They were able to reprint her that. So that was great. That was great. And she's also doing well, so shout out to her. But yeah. We're seeing these developments, but as you can see, they're usually more for hollower organs. We're talking about bladders, we're talking about tracheas. But when we get into more of like the big boys, the organs that people need quite often, kidneys, livers, those are much more dense organs cellularly. Like you just have more cells per like square meter, and they also have sometimes more complex jobs. So it's more difficult to like print organs like that. Again, we're on our way, but we're not quite there yet. There's this new printing method called HITS Bio, which stands for High Throughput Integrated Tissue Fabrication System for Bioprinting, mouthful, and it allows for like the stacking of spheroids, and essentially spheroids are bioinks that are very cellularly dense. So again, when we start talking about organs like the kidney and the liver, we might need bioinks more similar to spheroids, and allows and usually like when you stack spheroids, it's a researcher kind of like doing that all manually, like stacking it themselves, but like HITS Bio allows them to basically use like machinery to take multiple nozzles to like stack multiple steroids quite quickly because they're using like digitally controlled nozzles instead of a single one. And this is currently happening at the Ozab lab at Penn State, and they're claiming that it's making it genuinely 10 times faster. And also, cell viability looking good. Like HITS Bio right now has above 90% cell viability on average, which is great, guys. Like that's great.
Let me tell you. Let me like once again, these cell viability numbers will have you see it red for real. So that's actually really good, especially once again when we're thinking back to what I was talking about, like biodegradability, biocompatibility. Like once again, can the cells reproduce and integrate into the new living environment without literally dying on impact, basically?
I understand those cells, honestly, but yeah. So yeah, it's definitely like sped up bone repair in trials, and they've even been using it in rat trials, and it's been able to be quick enough to develop tissue intraoperatively during rat trials, which means like during the surgery they are able to like develop tissue for the rat. So like that's mad quick, and that is very good news. So yeah, it's looking up. It's looking up. Right now I think there's only one clinical trial for like 3D bioprinted human organ transplantation for like more dense organs. I don't know how that's going, and we'll hopefully hear more in a couple years, because again, guys, it really does take years. And another thing that's been like new on the human side of things is I keep hearing about 4D bioprinting.
Ooh. We're elevating.
Okay, a little fancy. So essentially, like 3D bioprinting is static, and like yes, like these cells are alive and they're able to proliferate, but they're not necessarily responsive to their environment, aka the human body. So basically, researchers have been working to create stimuli that are like more researchers are working to create organs and tissues and organelles that are more responsive to stimuli. So these are usually going to be partially made with stimuli responsive materials / polymers, so either SRMs or SRPs. And it helps like create technology that can both grow, repair, create, like you get a cut on your skin, then white blood cells come and patch it up, So like 4D bioprinting is more so working towards making these tissues, organs, organelles work like our own, which is only getting us closer to, again, being able to integrate them in both the research and the clinical side. But yeah, to make it truly integrate, there needs to be like a vascular network for oxygen and nutrient supply for both 3D and 4D bioprinting, just for like, again, bioprinting as a whole. So like that's another thing that they need to be able to work out in order to start integrating these things more into human life, animal life, because as you guys have already seen, the advancements they've been able to make are great and incredible, but that's what I love about science. We can just keep moving up.
Yeah, for sure. It's very complex what's being done. So trust that we're talking about it very lightheartedly, but it really is such a huge scientific advancement. But yeah, if we want to get to the level where we're creating hearts, we're creating, once again, organs that people really, really need on the organ transplant list, like that vascular network, allowing for more complex interactions. I feel like cellular plasticity is another thing. So we're on our way. We're on our way. So it's definitely very, very exciting. And the last guiding research question are, what are the ethical concerns that may arise? Because with any new technology or innovation, there's a lot of people using it for good, but there are a lot of moral conundrums that come up, whether that be religious, moral, and just like value based systems. Are people being exploited? Are there inherent biases encoded into them that society already kind of has? Like, there's just a lot to be considered. Um, Main one is always main one will always
Of
be
course,
money.
like especially when we are talking about like the U.S. health system in particular. Just to give you guys more understanding about like the transplant process, at least for U.S. transplants. If you're looking for an organ, you usually join a transplant list, but those are usually state by state, and there's usually like a max amount of lists that you are allowed to join. But wealthy people do tend to get transplants earlier in their journey than people who are not wealthy because they are able to get on more lists and increase their likelihood, very lottery ticket like, of being picked for an organ transplant. And I feel like that trend is just going to continue when we are talking about new scientific advancements. I mean, we're seeing it with CRISPR and sickle cell. Like the quotes that people are getting are outrageous, impossible, very much bankruptcy level quotes for how much these like life saving medications, interventions, and treatments are going to cost. And I feel like, similar things are just going to keep coming with these 3D bioprinted organs, tissues, organelles. Like, it's going to be incredibly expensive to get one, without a shadow of a doubt.
For sure. We often see with newer innovations that end up becoming commercialized that their initial cost is really, really, really high. And then over time, it gradually comes down. But that initial kind of market launch is definitely going to be geared towards wealthier individuals that can, from privatized firms that can actually be able to afford to use that technology. And another thing that I think is something to be considered is also, and this is more so inspired by like Golden and I have been watching a show about black markets and stuff like that. It almost makes me wonder. I know that there are a lot of people who are doing black market transplants out of the public eye, and it makes me almost wonder if people are going to create almost like shadow laboratories as well, start harvesting cells
For
illegally and unethically, and
sure.
try to create these 3D biological networks on their own. I mean, it requires very sophisticated technology. So at this point, it's probably very non existent because at the end of the day, like, you just need very, very expensive machinery that people would probably raise an eyebrow if it went missing to actually be able to create, and it requires so many steps in the process. But I could definitely see some criminal rubbing their hands together, like, and I know there's already a lot of people who go outside of the legal system because the legal system takes so long to get an organ. So we're already seeing wealthy people kind of pay out of pocket to be able to access organs that weren't necessarily harvested legally. And so I see that happening with this too as well.
Yeah, I for sure. I mean, even when the journalist was like diving deep into how people were getting these organs illegally, there was always a professional.
There has to be. There has to be
a doctor, like someone who has access to these things. So yeah, unfortunately, I do think that is gonna come with the territory. If you're going to make something life saving that is expensive, if you're going to make something life saving inaccessible, which I'm not just talking about 3D bioprinting, like, obviously people are going to find other ways to get it, period, point blank. And I think another issue that is a little bit away from just, again, like our regular issues with capitalism is the complexity of the donors, which is something that we actually talk about a lot in bioethics course, is one, donor cell ownership. Like, we see what happened with Henrietta Lacks. If you don't know, there was a low-income black woman whose cells were used without her permission to continue research on, and she never got paid. Her family never got paid.
Only recently they got a settlement.
But like her immediate family at the moment did not get paid. She succumbed to her illness and didn't even get to see like the research that came out of her own cells. And like there's an issue that like that may just come up as an issue later on too. For example, like if cells are donated to science, like do they have any control on what that's used for, how many cells are proliferated from those cells, like if cells are donated to create an organ, like can they only be able to create that organ itself, or like are they just allowed to do whatever they would like? Like there is gonna be definitely some messiness, some gray area when it comes to like donor cell ownerships and like having control out of that, and especially when we get to stem cells. And if you guys don't know what stem cells are, they're basically cells that still have the capacity, well, depending on the stem cell, but some stem cells still have the capacity to turn into any other cells. Like they can turn into neurons, they can turn into liver cells, they can turn into kidney cells, and oftentimes stem cells are what are used in a lot of just scientific research, period, but especially for something like 3D bioprinting. However, most stem cells that we currently use in research do come from embryos and fetuses, which, again, when we are thinking about morals, religion, and issues regarding that, just personal preference for certain things. And I think for a lot of people, there may be like a quote unquote ick factor, which is what we like to call it in bioethics, for certain things where you're not necessarily sure why you feel a certain way about something, or something may be foreign to you, but you know that you don't like it. And it might, pose issues, integrating things into society if people feel uneasy about them or not comfortable with that certain methodology.
For sure. I think even in my own lab, some of our donor human cells were, I think, they were from babies though. They were from, I know it was like an 18-month-old child. It would be like, because they label it like that. And it was, I think, their foreskin cells or something like
Right.
that. And so I know this is something I've talked about in like cell physiology, systems physiology, with like stem cells and the different kinds. And once again, the ethical concerns with using like embryonic stem cells. That is continuously a topic. And so obviously it bleeds into this topic as well. But yeah, I think the main ethical concerns for me with this is, once again, just access as always. And then also ownership, with people having, like, when it comes to things with body parts, it just starts to get really, really, really complicated, because it starts to be like, okay, who has ownership of what, and at what point does your ownership kind of stop? And it becomes the ownership of whatever scientific agency, whatever group of research scientists, whatever person the organ is now living in is, like, yeah.
And this might be more niche, but especially with these, again, like privatized biomedical engineering companies that are on the rise and will be.
Biomedical engineering?
Just watch out for those people.
I don't know.
Just watch out
like,
for
a
those
neuroscientist is
people.
always trying to talk about a biomedical engineer. I know what your people are known for. I know what your people
Not
are
too
known
much,
for.
okay? Things were different back then. But yeah, like another, like, again, more niche thing that may come up is like privacy, and donor privacy is like how much information you can actually find out about somebody by having like access to their cells, or maybe a demographic of people if you start collecting that too.
Oh,
and like
Lord.
and how much information you can find out about like the demographic of people, and like issues that may arise with that. So like, yeah, there are so many things to consider. And on like a more futuristic understanding of ethics, there may be things regarding like human enhancement that 3D bioprinting may end up bleeding into too. Like if we have the ability to generate all these different parts of our bodies, especially as the technology continues to advance. Again, something that they always say in bioethics is that the technology is advancing quicker than our laws are, and like, how are we going to deal with human enhancement, technological immortality, and just like these more, again, like sci-fi-ish, but not too far from a future for us topics.
Who knows? I mean, so much is always just a who knows until it happens. And I've seen with a lot of my favorite scientific discoveries in recent years where it's just kind of like I used to want to major in artificial intelligence. Don't play with me right now. But with many things, like, once again, it progresses at such a much faster rate than humans can regulate. But also, I think science sometimes suffers from the flip side, which is it doesn't progress as quickly as either A, society needs it to, or as people want it to. And then there becomes like this kind of stagnation and distrust and just general animosity, because it's just like, why have these things not worked yet? Why are these things not commercialized yet? If you guys are saying that you're advancing the human condition, like, why hasn't it come to that point yet? But once again, I know we've reiterated that multiple times in this episode, but science really is lengthy. Science takes time, but for good reason, because at the end of the day, you don't want people just putting any little thing into your body saying, hey, I created this new method of 3D bioprinting, and I'm just going to make this thing, and I'm going to harvest the cells, and I'm going to print it out, and then I'm going to transplant it into you, and, check back in with me in 5 years. Hope you're still kicking. Like, we would hate that if scientists were just running around doing the experiments that we used to allow them to do. Cue our last episode about phrenology, where they were doing any and everything. Just any and everything. So I think it is a good thing that we have such a long research process, and that we have all of these built-in critical checkpoints that people really need to meet before we allow this technology to be adapted for humans.
Because it's definitely in the eyes of billionaires, which is not great. I mean, as you guys have already seen, Zuckerberg, Musk, like Gates, like all these big brand names, like they have already put stake and put their money into neurotech, and I think there's nothing a billionaire is more obsessed with than his own mortality or her own mortality, girl boss. But I feel like 3D bioprinting will definitely be the type of thing that is immediately going to be in the eyes of people who are trying to capitalize off of it, and who are more so worried about the money-making part more than the saving lives part, for sure.
Yeah, that's why it really requires good people doing good science at the forefront of movements like this. So I remain hopeful, but at the same time, it's always important to keep a critical eye and make sure that these are really good actors who are investing in these technologies and these industries, because otherwise, once again, we're going to see it only be for the wealthy, and we're going to see it not be used in the best way for the people who actually need it. And that's once again, over 105,000 people on the transplant waiting list, and the people who are dying because they can't access organs. So now that we have done the science for today, let's get into our bits of BS. And once again, bits of BS are things that we went through getting our bachelors that we are now reflecting on as recently graduated ladies, that really tried us. Moments that really show how you gotta get through some BS to get to the BS. Gold, I'll let you go first.
Honestly, and let me just preface, I do not mean this in a rude way to who this is about, but it really was my 13th reading that day. So essentially, I love an early morning lab, which may be an unpopular opinion, but I'm down for an 8 a.m. lab. I always took the 8 a.m. bio labs.
I don't know how I feel about that, but I mean, I don't like staying late though. So I'm the type of person who I would take the earlier afternoon classes, but I didn't like it. I
don't know, for something about biolab, it just chem lab, that's a different conversation. But biolab, I used to be up ready to run that group before the Marines. And I think it came to a certain point for 8 a.m. labs, people were just late so often, oversleeping so often.
Oh, that might have been me.
That if you came into the class 20 minutes late, it was you didn't come at all. Basically, if you came after 8:20, you would have to remake the lab anyway. So it was no need to rush in 35 minutes late, because that would be that was the new cutoff, which again was fine and dandy for me. But it's just one day I'm in biolab, I come in, I see my 2 group mates, but I don't see my other group mate, and time is ticking. 8:17. It gets to 8:18 or so, 8:19, and I see this person bust through the door, which I'm honestly glad about. Okay, they're a good worker. We'll probably get through the lab quickly, but as they start speaking to me, Ileana, when I tell you that breath is kicking, that breath is performing black belt jujitsu on me, and honestly,
goodness.
they're not even that close to me either. Like,
wait, that's insane.
That's the thing that's killing me. Now, like,
first of all, smelling the stench from across the lab at my 8 a.m. like that would be my 13th reason. Actually, that would have killed. Because I didn't even want to show up, and now you want to harass me, like with your terrible breath.
Harass me, just nasally harassing me, and just like even on the days where I used to wake up mad late, if there was one thing I was going to do, it was brush my teeth. And listen, like he busted in the room like minutes, seconds from not being able to participate in class. So I guess he ain't have that time. But like when I tell you, Ileana, that was a ridiculous thing to experience for 3 hours. Like I was already mad. And now your breath is ruining my already bad day. And honestly, I'm not even gonna lie, he was not the only person to put me through an experience like that. Like, when you are working in STEM, you're gonna smell that stench every once in a while. I'm not even gonna
Who are you telling?
It's not always cute.
Who are you telling, bro? Yeah, them STEM bros be smelling like.
Shout out to the comp sci majors for real.
Them comp sci ladies, stronger woman than I will ever be, for real.
The strongest soldiers. Okay.
Okay, my bit of BS is really more so about freshman year. Was I tweet? There were professors who probably put me through more than this man, but it was my freshman year, guys, okay? And he had been my lab coordinator. This was a professor that had been my lab coordinator for my chem class the first semester, but I didn't actually like have him as a professor. He was just the overall coordinator. And even then I could sense the vibes were off, but whatever. And then the second semester, he actually was my professor for Orgo. And this man is a character, okay? Like, such a character. And I think my bit of BS was really that, like, he used to know he was doing us wrong with the test that he created. And I swear, me and my friends swear he would go missing after the test. Like, literally, these tests used to be like, I would like the type of test where you like open them and you start laughing immediately because it's just like,
Just go ahead and go to the back.
Like, I used to just be in the back tired, just laughing. I'm sure the people around me thought I was insane. But yeah, he would pack his stuff up so quickly, and then I swear to God, you would not see that man on campus. Like, I would be like, we would literally be like, and Mevins knows to stay in his office and to stay away because he knows we're coming from. I think one time I even went to his office, he wasn't there. Like, he knew
they
to
know
get
it's not safe.
He knew to get out of Dodge for real. And I used to be
Orgo lab professors, like the ones who are overhead the lab, like they know it's not safe. Like,
and I used to be, really mad at him. Like, oh my goodness, he was on my number one hit list for real that semester. I remember almost jumping some random man in my parking garage because I thought it was him. Like, oh my God, it was not funny. It was not funny at all. So that was one bit of BS. But I got an A in that class. I got an A in both classes. So I guess it ended up okay.
One thing an Orgo professor is going to do is stress you out. Like, honestly, there was like an Orgo lab professor who used to do the opposite. Like, she would disappear right before a test. Like, she would host the office hours and not show up. People started protesting. Like, that rate my professor was unreadable. Okay? they was out here saying things that weren't okay. Like, I think the school had to like tell rate my professor, you have to take some of these down. You have to take some of these down. Like, she again hosted an office hour, everybody show up but you. Because you know the test is soon. Don't do that. Don't do that now. Like,
LOL. These teachers be trying to get out of dealing with angry students. And, like, I get that sometimes it's not that deep and it will be okay. But sometimes they're like, you're playing with me. But thank you guys for watching. We're about to end the episode. But of course, always reference the required reading. We do so much research in order to be able to come back and bring you guys the latest and greatest scientific innovation. So if there's anything that you're curious about or just want to read up more on, if you want to check our sources, go right ahead. They're always linked in the description box. Make sure to like, comment, and subscribe. Show support for your obviously favorite podcast. Like, come on, guys. Your favorite STEM besties. But yeah, thank you guys for watching, and we'll see you in the next one. Bye.